Mathematical model and sensitivity analysis of a parallel three-phase voltage source inverter. Abstract. Recently, there has been a great interest in grid-connected renewable energy resources such as photovoltaic, fuel cells and wind energy. Typically, parallel connected three-phase voltage source inverters are utilized in these grid-connected renewable energy applications. In this paper, modeling and control of a parallel three-phase voltage source inverter is considered. To set the stage, the inverter model is derived by defining the variations in the output DQ voltages and DQ currents as the system states. The variation in duty cycle is defined as the control input. The system control is implemented using two different control strategies, i.e., voltage control mode of the first inverter and power control mode of the second inverter. To optimize the system performance, the sensitivity analysis is applied to the inverter model. To verify the eigenvalue analysis, time domain simulation is used to determine the effects of controller and parameter variations on the system stability. Keywords: parallel inverter, sensitivity analysis, eigenvalue location, SVPWM. Introduction. The surge of applications of power electronics in industrial, commercial, military, aerospace, and residential areas has driven many research studies in this subject. 1. The objective of these studies is mainly to obtain highly reliable and efficient power electronic components with low cost and compact size. In addition, power electronics play an important role in the advancement of distributed energy resources. 1. Due to their environmental and economic benefits compared to large power plants, the reliance on distributed power sources, such as fuel cells, wind turbines, and photovoltaic systems has increased in the recent years. However, these sources do not necessarily generate the desired rated voltage and frequency. Therefore, a voltage source inverter, VSI, is required to be used as an interface between the distributed energy source and the main grid as shown in Fig. 1. Distributed power sources in microgrid can operate in parallel to the grid or in the island mode too. Consequently, many research has focused recently on the use of a set of inverters connected in parallel. Parallel connected inverters enable the load current to be shared among different distributed resources and the main grid. As a result, the reliability of the whole power generation system will be improved. Due to the existence of large number of power converters, the stability problem becomes increasingly important in distributed energy systems. To improve the stability and the performance of the distributed energy resource, small signal modeling of the parallel voltage source inverter system is considered. 2. 3. There are many research papers provide an extended review for control techniques of parallel inverters. 4-6. The control strategies may be classified as centralized and decentralized control strategies. 4. The centralized control strategy has many good advantages. For instance, the current sharing is forced at all times even during transient, and different power rating inverters can be connected without changing the control structure. The system may also be easily maintained and replaced. However, this strategy has a few serious disadvantages. One of the major disadvantages is due to the reference voltage and current signals that have to be sent to all inverters in the network. This requires a high bandwidth communication link in the system which is sensitive to nonlinear loads. On the other hand, master/slave control method gives a good load sharing and synchronization. The main disadvantage of the master/slave method is that it is not redundant since it has a single point of failure. Furthermore, there are excellent features of the current/power sharing control technique. They have a load sharing with a very good transient response and less circulating current between the inverters. This technique has some problems such as, it is not easily expendable and it requires an interconnection which make the system less reliable. The distributed control strategy, on the other hand, is based on the rotational reference frame rather than stationary reference frame. A current sharing in the system is provided in steady state and during transient. Lower communication bandwidth is needed. However, this strategy is not appropriate for unbalanced systems. Droop control method has many desirable features such as expandability, modularity, redundancy, and flexibility. There are as well some drawbacks such as slow transient response and possibility of circulating current. These reviews lead to the control techniques of parallel inverter, which are classified according to mode of operation, and these techniques still require development to overcome some challenges. For instance, a sensitivity analysis should be carried out to achieve system stability. In this paper, a general control system model with two different control modes of parallel operated inverters are discussed. The average model of the parallel operated voltage source inverters is based on a phase leg and small signal model. Then D is more than 400, these complex eigenvalues become two real poles which are less influenced by D. Therefore, D is selected to be 400 or any value more than 400. In Fig 5, Gi is increasing from 0 to 4000, while all other parameters are set to be constant. There are two real eigenvalues influenced by Gi. When Gi is increasing from 0 to 400, one real pole at origin point moves towards the other real pole that is very close to the origin point and become a pair of complex conjugate poles with more stable because KIDP2IS increased from 0.01 to 1, this pair of complex conjugate eigenvalues becomes a pair of two real eigenvalues with less overshoot and oscillations. Furthermore, when KIDP2IS increased from 1 to 100, one of these real eigenvalues moves quickly towards origin point, which reduce the system stability, and another real eigenvalue moves far away from origin point towards LHP. This shows the stability of the system is less sensitive to this eigenvalue. So KIDP2 is set to be 1. Improvement of damping ratio. This pair of complex conjugate eigenvalues with Gi more than 400 becomes two real eigenvalues with less sensitivity to the variation of Gi. So Gi is set to be 400 or any other value more than 400. Conclusion. In this paper, control strategies of two inverters operated in parallel were considered. The control strategy of the first inverter was based on the voltage control mode, while the reference value of the three-phase output voltage's peak is set to be 170 V. Initially, the active and reactive power of the second inverter are 10 kW and 2 kVAr respectively. These values are reduced by 50% after 0.35 seconds. The reference frequency is set to be 50 Hz. The simulation is run for 0.5 seconds and results under two different control strategies which are carried out and used to verify the eigenvalue analysis. The time domain simulation with L variation is shown in Fig 9. When L is set as 4 mH, the active power of the second inverter converges to high stable state with small oscillation compared to the two other values. From these simulation results, the system has large oscillation when this parameter is decreased to 0.63 mH. The stability of the system is reduced with high overshoot when L equals 10 mH. This is almost consistent with the frequency domain analysis.